Introduction to Taylor Polynomials. Objectives. By the end of this lesson, you should be able to describe why Taylor polynomials are useful, explain the significance of being near the center of a Taylor polynomial, and explain the relationship between a Taylor and Maclaurin polynomial. Alright, so before we start a formal definition of a Taylor polynomial, I want to discuss why they're useful. And to begin that conversation, I want to get into a little bit of a discussion. So if I put this graph up on the board here on this xy plane and asked you, what function is this? What might you tell me? So notice there are no tick marks on this xy plane. So maybe your first guess is that this is the function y equals x. It looks like it has a perfect slope of 1 over 1. But again, we don't have any units drawn on this plane. So now what if I zoomed out and I told you that that xy plane that I showed you was actually just this portion of the graph that's really this graph depicted here. So if I asked you what function is now represented, maybe you might tell me, well, now this looks like a cubic polynomial. So it has these two turning points, this minimum and this maximum, and it sort of looks like it could be a cubic polynomial. So finally, what if I zoomed out even more and told you that that original graph that I showed you was originally the graph of y equals sine x? So here you can see this is a graph of y equals sine x, and that original graph I showed you was sine x zoomed in really, really close around the x value of 0. So it looked like the sine function was actually just the line y equals x because I was so close to the origin at 0, 0. And it turns out that y equals x is actually the linear approximation, the equation of the tangent line, to the graph of sine x at equals 0. And then that next picture I showed you, that was this representation here of what looked like a cubic polynomial. And a cubic polynomial would actually really accurately approximate the sine function near 0, but it would have to be a really specific polynomial. So now I want to talk about how we're going to use polynomials to approximate other types of functions that aren't easy to evaluate without a calculator. So we already discussed Taylor polynomials in brief when we looked at linear approximations, because a line is an example of a polynomial. So now we're going to generalize this, and we're going to find higher degree polynomials that are going to very accurately describe other types of non-polynomial functions around what's going to be called some center point. Alright, so now let's try to get a little bit more technical about what polynomials are going to approximate the sine function near 0. So right at 0, 0, this red line is the linear approximation, y equals x. And we already know how to find a linear approximation. We do need the derivative of sine x at 0, and we need the point 0, 0, and that's going to go ahead and give us our linear approximation. Been there, done that. So now it's about, well, how do I find out exactly which higher degree polynomial is going to approximate the sine function further and further away from 0? So this red line right now, if I were to try to approximate what's happening on the sine graph right here at 2, and I try to use this linear approximation, so the linear approximation would give me out a y value of 2 when clearly the sine function is down here. That's a value a little bit less than 1, so this is a huge margin of error here. So what I want to do is try to find a higher degree polynomial to try to find the best possible scenario and get the least amount of error. So here is a cubic, and this cubic is x minus x cubed. And so now the question is this a good cubic polynomial to approximate the sine function? And hopefully you're thinking, no, it's not really that great of an approximation unless I'm pretty close to 0. So this green curve, it does hug the sine function near 0, maybe up until about right here, maybe until about negative 1/2 and 1/2. It's pretty accurate, but over here at 2, well, if I wanted this sine value right here, which again is a little less than 1, I would actually, if I suck 2 into x minus x cubed, end up getting a value way down here that's not even on the screen. So it's a really, really big margin of error in this particular cubic polynomial. Alright, so now how about this one? So the black graph is again the sine function, the red line is y equals x, And what if I try x equals 1 over 10x cubed? So the previous one was just x minus x cubed. Now I've added this coefficient 1 over 10 to be in front of x cubed. So this was arbitrarily chosen. I'm just kind of guessing and checking right now. So now this cubic polynomial gets pretty close to the sine function, and that value that we looked at earlier was at 2. So again, we would be trying to find this value on the sine function, right about here. Maybe that's 0.8 is the actual value. And if we instead plugged 2 into this cubic polynomial, we would get out this value here, and that's not too bad compared to the value I'd get out when I substitute it into y equals x. I'd get out 2, and then here's my margin of error. So this error using the linear function is a lot worse than using this new cubic polynomial here with that difference in coefficient to be 1 over 10. So this is a much smaller error. This error is going to be less than that one up there. And that was using a cubic polynomial. Alright, so now here's the black graph is the sine function. And so far we've used the line, but you'll notice that this image doesn't have the line anymore because the line stopped being useful once I started getting further away from 0. So this red curve here is the cubic function x minus 1 over 6 x cubed. So a little different than the one we just previously looked at. And you'll notice that that red graph is pretty close to the sine curve, all the way up until maybe about, let's say 1.3 here, and then over here at negative 1.3. They look like they are almost identical. But nobody said we had to stop at cubic polynomials. We can also try a quintic polynomial, so polynomial of degree 5. And this green curve here is actually the quintic, x minus 16x cubed plus 1 over 120 x to the 5th. And you'll notice that this green curve hugs the sine function just a little bit further. So maybe where the cubic sort of broke down at being very accurate around 1.3, so now this quintic is hugging it all the way up until maybe a little less than 2, like 1.9, and then over here at negative 1.9. So maybe it seems reasonable to conclude if I increase the degree of the polynomial that I use to approximate the sine function, I may be able to approximate sine further and further away from that original 0, 0 location that I started looking at to begin with. But where are these numbers coming from? Negative 1 over 6 or 1 over 120? Alright, so in this last example, we ditched the linear function. That stopped being accurate really, really close to 0 in a really small window. And then we ditched the cubic polynomial because that broke apart pretty early as well. So in this image, the black graph is the sine function, and the red graph that you see is the quintic, which was pretty good. But if we choose this 7th degree polynomial, given down here, x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040, that's a really good approximation of the sine function all the way out until, really, really close to negative 3, and then over here at positive 3. So between negative 3 and positive 3, this 7th degree polynomial looks identical to the sine function. So the higher we increase the degree, the further and further we could go away from that center point I have here, 0. So it turns out that the sine function can be approximated by using this particular sum with alternating terms. So x minus x cubed over 3 factorial plus x to the 5th over 5 factorial all the way up to, so here's the alternating portion of the term, and then here's the general term, x to the 2n plus 1 over 2n plus 1 factorial. So that's how I'm going to keep finding those coefficients. And notice that we only used polynomials that had odd degrees. So x to the 1 was the first one, and then x to the 1 minus x cubed over 6, because 3 factorial is 6, and then x to the 5th, and then we use a 7th degree polynomial. So it turns out that the sine function can be approximated by using this, what is called a Taylor polynomial. Okay, so now let's sort of formalize what we just did. So in general, we found the nth Taylor polynomial of f of x centered at x equals a. So the f of x in the previous discussion was the sine function, and the center was at x equals 0. But we can generalize this. We can find the nth Taylor polynomial for any function f of x centered at any particular value by using this formula. So the notation for the nth Taylor polynomial is t sub n of x equals f of a plus f prime of a over 1 factorial times x minus a to the 1 plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a to the 3rd power. And hopefully you can see the general term would be f to the nth derivative of a over n factorial times x minus a to the n. So it looks like a daunting formula. I absolutely agree. But it's not that bad. So here, this is the first derivative. What goes beneath it is 1 factorial, and then x minus a to the 1. So first derivative, 1 factorial, x minus a to the 1st degree, plus the second derivative at a over 2 factorial. So second derivative, 2 factorial, x minus a squared, plus the third derivative at a over 3 factorial times x minus a to the 3rd power. So we're going to stop when we want to find the nth Taylor polynomial. We have to find the nth derivative at a over n factorial times x minus a to the nth power. So in order for this formula to be valid, we have to have all higher derivatives exist in some interval around x equals a. And when a equals 0, so when the center value is 0, t sub n of x is called the nth Maclaurin polynomial. So there's a special name when the center of the Taylor polynomial is 0, it's now called a Maclaurin polynomial. And we also have a special title for n. N is called the order of the Taylor polynomial. So a first order Taylor polynomial is just the linear approximation or tangent line at x equals a. And let's think about that for a second. So a tangent line, we use y minus y1 equals m times x minus x1. And we fill in our values. So our m is always equal to f prime of a, and our point is a, f of a. So y minus y1 f of a equals m, which is f prime of a, times x minus a. So if I just move this f of a to the other side, y equals f of a added to the other side plus f prime of a times x minus a. Hopefully you can see that's just stopping right here in the Taylor polynomial formula. F of a plus f prime of a, well 1 factorial is 1, times x minus a. So times x minus a. So we've already done an example of a Taylor polynomial when we did linear approximations, but now we're trying to go further and find higher degree polynomials that can approximate any function we want. So here are a few expanded Taylor polynomials centered at x equals a. So even though it's kind of uninteresting, we do discuss the idea of a Taylor polynomial of order 0, which is really just f of a, just the function value at a. And the first order Taylor polynomial, as we mentioned, is the linear approximation. So f of a plus f prime of a times x minus a. So what we're missing from that general formula is this was over 1 factorial, but that's just 1, so we're dropping it. The second order Taylor polynomial, so it's all the same portion of the first order Taylor polynomial plus the second derivative at a, all over 2 factorial, well that's just 2, times x minus a squared. And the third order Taylor polynomial that's been expanded here, so it's all the portion of the second order Taylor polynomial plus the third derivative at a over 6. So 6 is a simplified 3 factorial, because that's 3 times 2 times 1. And then times x minus a to the 3rd power. So this is just to show what they look like expanded. So if you were asked to find the third order Taylor polynomial, you'd start with this equation here, and we'd have to substitute in everything that's missing. So f of a, f prime of a, f double prime of a, f triple prime of a, and that would complete our Taylor polynomial of that order. So as we wrap up this introduction on Taylor polynomials, I want to go over a few observations that we've looked at so far. Taylor polynomials match the function that they're trying to approximate perfectly at the center, x equals a. So every single Taylor polynomial, it doesn't matter what order it is going to exactly match the function at x equals a. But the Taylor polynomials, they lose accuracy as we move away from the center. So as we move away from the center, the error from the original function to the Taylor polynomial is growing bigger and bigger. But Taylor polynomials gain accuracy as we start to add more terms to the polynomial. So as we started to increase from a cubic on that example to a quintic to a 7th degree polynomial, we were gaining accuracy further and further away from the center. So now let's talk about where we're going, some motivating questions. So is there a systematic way to come up with the coefficients of a Taylor polynomial for a given function? So at first, on that sine function, we just sort of guessed any cubic polynomial, but we want to come up with a systematic way to find those coefficients because guessing isn't very efficient. The second motivating question is, how good are these Taylor polynomials going to be? What is the error between a Taylor polynomial and the original function we were trying to approximate? Number 3 is, can we extend the interval on which the Taylor polynomial is a good fit? So is there a way that we can get further and further away from the origin and make sure the Taylor polynomial is going to be a really, really good approximation? And then if we use infinitely many terms, can we match the function exactly? And to add to that, what does that even mean? Because polynomials are finite. They have a finite degree. So is it even going to make sense to talk about adding and using infinitely many terms to potentially match the function we were trying to approximate exactly? So these are going to be our goals for this section, is we're going to try to answer these motivating questions regarding Taylor polynomials.